Welcome back to The Explainer. I am absolutely thrilled to guide you through today's topic because we are going on a really fascinating journey. We're going to break down exactly how we transform raw, messy data into pure, actionable insights. Think of it kind of like building a high-performance machine. Today, we are popping the hood on the engine of quantitative research.
Just look around us. We are literally drowning in data. Every click, every purchase, every little decision generates numbers. But how do we actually make sense of this overwhelming avalanche of information without getting completely lost in all the noise? More importantly, how do we find actual, verifiable truth in a world that often feels incredibly chaotic?
There's this fantastic quote from researcher Weng Marc Lim's 2025 overview of quantitative research that hits the nail on the head. He points out that we live in a DVUCA world: disruptive, volatile, uncertain, complex, and ambiguous. In an environment like that, you simply can't rely on gut feelings. We need a reliable, rigorous machine to process reality. The stakes are just too high, which completely elevates the urgency for accurate, timely, and empirically sound research.
So here's our game plan for today. We're going to cover why we need quantitative research, designing your insight engine, gathering the raw data, preparing the fuel, the 4 levels of analysis, and we'll wrap up with testing the truth.
All right, part 1, why we need quantitative research. It really is the ultimate tool for finding clarity.
Let's set the foundation here. Look, qualitative or non-quantitative research is fantastic for the human narrative, right? It totally embraces subjectivity, human experiences, and thematic exploration. But quantitative research? That's a whole different beast. It is all about measurable variables, numerical data, and objective hypothesis testing. It gives us that empirical rigor and the scalable framework we need for large-scale proof. It's exactly how we isolate variables and pinpoint quantifiable trends.
And here's the crucial thing. We aren't just doing math for the fun of it. We built this insight engine to generate the 4 Ps of data analysis. We want to extract patterns to see what's currently happening, diagnose problems to know exactly why it's happening, make predictions about what's going to happen next, and ultimately offer prescriptions. That's the real gold, actionable strategies on what we should actually do about it. Those 4 outputs are the entire reason our engine exists in the first place.
Moving on to part 2. Designing your insight engine. Think of these as your blueprints for empirical rigor.
Now that we know why we need it, how do researchers actually design this machinery before they start pulling in data? Well, building the engine means making some pretty tough trade-offs based on your resources. Do you collect primary, fresh data that's tailored perfectly to your exact question, but spend a massive amount of time and money doing it? Or do you use secondary, existing data that's cheap but might not align perfectly? Do you take a cross-sectional snapshot, just one moment in time, or track things longitudinally over weeks or even years? And do you manipulate variables in a highly controlled experiment to prove causality, or just observe non-experimental, real-world conditions? Every single one of these choices fundamentally shapes the kind of truth your engine will eventually spit out. Which brings us to part 3, gathering the raw data. It's time to collect the raw materials.
We have our blueprints, so now we need to acquire the data itself. This right here is the fuel for our machine. But listen, bad sampling is exactly like pouring dirty, contaminated fuel into a high-performance sports car. It will completely destroy your system. Random sampling is the absolute gold standard because it gives everyone an equal chance of being included. That minimizes selection bias and maximizes how well your findings actually generalize to the real world. Non-random sampling, like just surveying people who happen to be convenient to you, sure, it's way easier, but it heavily risks biasing your entire set of results.
So how much of this data fuel do you actually need? Well, there are incredibly complex mathematical ways to calculate sample size using inverse square roots or Monte Carlo simulations. But a super popular quick rule of thumb is the 10 times rule. It basically suggests your minimum sample size should be at least 10 times the maximum number of predictors pointing at a dependent variable in your model. It's just a really great baseline check to ensure your engine doesn't stall out from a lack of data.
All right, part 4, preparing the fuel, or as I like to call it, cleaning up the mess.
We've gathered our data, but as any researcher on the planet will tell you, raw data is a mess. It is full of errors, weird blanks, and bizarre responses. We absolutely have to refine it before the engine room can process it. First up, we handle missing data. Do we delete the incomplete rows entirely or impute the average? Second, we manage outliers, and I always kind of smile at the academic terms here.
Statisticians use things like Mahalanobis distance and Tukey's fences. Sounds like a sci-fi measurement and maybe a neighbor's landscaping choice, right? But they are actually brilliant mathematical tools to wrangle wild data points. Finally, we check our assumptions, making sure the data is normally distributed and linear.
During this prep phase, we also have to filter out some serious contaminants. First up is common method bias. This happens when the actual method you use to collect the data is what causes a false correlation. A classic trap here is measuring both your independent and dependent variables in the exact same survey, using the exact same 7-point Likert scale. The survey method itself creates a bias.
The second contaminant is social desirability bias. Let's be real, people naturally want to look good. If you ask sensitive questions, respondents will either unconsciously or totally consciously skew their answers to appear more favorable. To keep the fuel pure, researchers use anonymous surveying, forced choice items, or specialized psychological tools like the Marlowe Crown scale to detect and adjust for those exaggerated responses.
But the final and arguably most destructive contaminant is endogeneity. This is a total engine destroyer. It happens when there is an omitted, completely unmeasured variable that is secretly influencing both your cause and your effect, making you draw totally false conclusions. To fix this, researchers basically have to act like detectives, using control variables or really clever instrumental variables to isolate the true relationships.
Part 5. The 4 levels of analysis. Let's step inside the engine room.
The blueprints are drawn, the data fuel is clean and perfectly refined. Now we fire it up. You can actually see the escalation of insights happening right here. We start at the descriptive level, calculating means and standard deviations just to summarize what happened. Then we level up to diagnostic analysis, using ANOVA or factor analysis to understand why it happened. Then we hit predictive, running regressions or time series forecasting to see what's going to happen next. Finally, we reach the pinnacle, prescriptive analysis. This is using optimization algorithms and decision trees to tell governments or companies exactly what they should do about it.
And finally, Part 6. Testing the truth, quality control and avoiding traps. We have finally reached the end of the line. We have our insights, but are they actually true? We have to test them. Every single insight must survive a brutal scientific gauntlet. You formulate your hypothesis. You boldly choose your significance level, usually setting a very strict 5% margin for error. You run the complex statistical calculations to get your p-value. And finally, you make a hard decision. Do the numbers actually give you enough evidence to reject the null hypothesis or not?
But here's where things can go terribly wrong. Have you heard of data dredging or p-hacking? This is the ultimate quality control failure. It's basically when a researcher tortures the data until it confesses. They just run test after test, manipulating variables endlessly until a non-significant result magically crosses the threshold of significance. It's a massive methodological failure, which is exactly why pre-registering hypotheses is absolutely vital today.
And honestly, even if you don't p-hack, errors still happen. Most of us know type 1 and type 2 errors, your basic false positives and false negatives. But what is truly fascinating to me are type 3 and type 4 errors. Falling into a type 3 or 4 error means you actually got the complex math completely right, your statistics are absolutely flawless, but you completely botched the interpretation in the real world. You rejected the null for the wrong theoretical reason, or you wildly overgeneralized your findings to a population that wasn't even in your sample.
So there you have it. We have built the insight engine together, from the very first blueprint to the final quality control check. We've seen exactly how quantitative research demands rigorous sampling, pristine data cleaning, and incredibly strict statistical soundness. So given everything you now know about the dangers of messy fuel, p-hacking, and those super sneaky type 4 interpretation errors, how are you going to look at the next data-driven headline that pops up in your feed? Will you accept it at face value, or will you look under the hood? Thanks for joining me on this explainer, and keep questioning the data around you.